And good afternoon, everyone. I hope everyone's having a good BUIDL week. To start, I am Eunice. I am one of the co-founders and GM of Monad Foundation. Today, we'll talk a little bit more about the Monad architecture and design and how it influences blockchain performance as it relates to Monad blockchain specifically. To start, a little bit of a history on the performance in blockchain. We're going to start at the very, very, very beginning with Bitcoin in 2009. When it was introduced as the first decentralized distributed cryptocurrency. Basically, a ledger for transfers and account management. Very, very simple, but it provided a lot of utility. However, really low throughput, 7 transactions per second. In comparison, and this is what everyone compares it to, VisaNet, which is the network for Visa transactions, is on paper capable of 65,000 transactions per second. In practice, I think it's actually a little lower. I think we see an average of 1,700 to 4,000 transactions per second. So we'll use that as kind of a metric for like real-world usage. All right, Bitcoin, great in theory, but in practice, maybe struggles for scalability, and this was in 2009. So in 2015, when Ethereum came about, it offered utility beyond payments, something distinct at the time. And I think no one really understood the capabilities of smart contracting and distributed applications until the years to follow. But it introduced distributed computation. It also introduced shorter block times, 12 seconds, and a concept of gas units, because with distributed computation, you may also need some units of utilizing that computation itself. So to start, 15 million gas units per block. So if we break this down into the 12 seconds for each block, it's 1.25 million gas per second. As a baseline reference, a simple transfer, like the very, very simplest base case of any transaction, it costs about 21,000 gas units. Sorry, not about, exactly 21,000 gas units. And around 120,000 for a simple swap, akin to a Uni V2 swap. So that's about, as listed here, about 60 transfers per second, or 10 swaps per second at the time of Ethereum's first launch. Still not great when you compare it to VisaNet. So in 2015 to 2020, when there was more adoption of smart contracts, more adoption of the early phases of DeFi, and then going mainstream with the first bull run between 2017 and 2018, and then into 2019, kind of hitting some frictions where, you know what, maybe the increase of 7 transactions per second to 59 still isn't sufficient. By the end of 2020, a lot of TVL was on Ethereum for obvious reasons. There just weren't as many networks to begin with. But that extends to today. So 97% of on-chain TVL is either on Ethereum or in Ethereum virtual machine compatible L1s. I literally checked this data on DeFi Llama 2 nights ago, so I guarantee it's accurate. Feel free to check my math there. In an answer to some limited throughput, limited performance on EVM, we had a couple of new blockchains go live. In 2020, we saw Avalanche. They had a or maybe still has a 3-chain approach where the C chain is where smart contracts occur, or transaction for smart contracts occur. It has about a 2-second finality, as well as 15 million gas for every 10-second interval. So a little bit better than Ethereum's starting point. That gets us to 1.5 million gas per second. And then BNB chain, which is essentially a replica of Ethereum with some updates to various configurations, now sped up from 12 blocks, 12-second blocks to now 3-second block times. And also increasing the gas per block significantly from 15 million to now 140. So that gets us to 2,000 transactions per second for simple transfers. Not bad, getting much closer to VisaNet. However, Ethereum may be rebutted. In 2021, they increased their max gas from 15 million to 30 million. And then again, just recently, 2 months ago, they increased it from 30 to 32 million. So some improvement, 2.67 million gas per block. It's still not enough, though, so that's why we're seeing different alternatives for scaling Ethereum, L2s being the prominent path forward, Arbitrum Optimism launching in 21 and then Base in 23. But bandwidth is still constrained. So enter Monad. In 2022, we were still realizing that there were a lot of frictions with scaling, and Monad research and development began in early 22. The thesis here has always been the same, is that Ethereum Virtual Machine is here to stay, that there's a lot of mind share already within this space, but there needs to be performance that is coupled with the demand. So, in realizing that users might benefit from a new design, Monad is a new L1 with a new implementation for the Ethereum Virtual Machine, which preserves everything. The focus, however, is on performance. And more specifically, the new stats here are 300 million gas units per second, along with half-second block times and single-slot finality. So this is quite differentiated from what we had previously been seeing with Ethereum and related L1s. The testnet is live as of 2 months ago, by the way, so if you haven't checked it out, I encourage you to do so. Not only that, but it is also maintaining decentralization. Right now on testnet, there are 72 worldwide validators, and the expectation is that that number continues to increase and diversify across the globe. Actually, on Friday, we did a throughput test, and hopefully this video shows up here. This video here, automatically playing. All right. Yeah, please, kick it off. Okay, so this video here is an 18-second video of the live throughput test here. You can see down at the bottom left is a TPS metric, and this is based on transfers alone. However, you can see that it significantly is able to process a lot of load over the course of the test. So sustained high TPS, high throughput on Monad testnet, which is pretty cool to see. So I think you saw some numbers there that spanned above 10,000 transactions per second. The block that I called out here, and if you want to look at it, there's links to the Monad block explorers. There's 2 of them that you could take a look at, which, again, half-second block times. So 5,000 transactions per second per block, 10,000 transactions per second. Okay, how are we able to do this? There's 4 key optimizations that Monad blockchain employs: asynchronous execution, parallelized execution, Monad database, MonadDB, as well as Monad BFT. Oh, sorry, forgot to cycle through them. We'll start with asynchronous execution. So this is also what we call decoupled consensus from execution. And the idea here is that you don't need to interleave both consensus and execution for block production, which is the way that most blockchains currently work today, where you need both hand in hand. Why is this inefficient? Well, again, let's take a look at Ethereum as an example. The top bar here is basically like a 12-second block time, let's say. Of that 12-second block time, the breakdown is that execution is just a tiny, tiny fraction of the time taken relative to consensus. And why is that? Well, if we think about what consensus is, it's network communication for all of these nodes across the globe. It's going to take time. Inefficient, right? Because, here's interleaved execution. Inefficient, again, because we're spending a lot of the block time just on consensus. Well, what about execution? In asynchronous execution, the idea here is to pull out execution from the hot path of consensus and block building. So now we're working towards a paradigm of 2 separate swim lanes. There's a consensus swim lane and there's an execution swim lane, both happening in tandem, in parallel, in a pipeline fashion. So the even greater version of this is expanding for any given block the time that execution can take relative to in previous cases where execution was just a tiny fraction of block times. Now, since they are running in parallel, we can utilize the entire block time, not just for consensus, but also for execution itself, which means more transactions can be processed in a given block slot. And yeah, quick comparison here. All right, for parallelized execution, and this is probably the one that a lot of people have been hearing about, there are other blockchains that are also employing parallelized execution as well, whether it's via the term OCC or STM, same thing. With parallelized execution, the idea is to be very optimized with the resources at hand. These days, a lot of the machines that we have multiple cores, and each of those cores can spin out multiple threads. Why not use them? Why are we using just a single thread to transact and execute transactions in serial order? We don't have to do that. So, just a quick rundown. In parallel execution, we're just going to take a look at let's just assume the very far left here is like transactions from top to bottom, and these are ordered canonically. And we're going to run through the transactions of the first 5 up here. In a standard blockchain, ordering them serially, executing them serially, we basically see this like transaction 1, 2, 3, 4, 5 is executed in this manner. Totally fine, works out great. In the parallelized execution view, now let's pretend that we have 3 resources, and we want to use all 3 resources effectively. So we can schedule the execution time for each of these transactions appropriately. We've got 3 resources. I'm going to schedule the first 3 transactions here. Note the bars are a little bit different in size because not all transactions will require the same amount of computation bandwidth. Okay. The red bar at the top is just going to emulate passage of time. So as time passes, the execution of transaction 3 completes. So we're going to add this idea of a pending result to a queue, and we're going to continue doing that. So now that the pending result has been posted, we are still waiting for the pending result from transaction 1. Even though parallelized execution allows for transactions to be executed simultaneously, we're still waiting to commit the new state of each of these transactions in order. So it has to wait for one first. All right, so we're going to just continue on with this, with this example here. I'm going to go back a little bit. Okay, so at this point, transaction 1 has finalized. I'm sorry, I bumped ahead a little too quickly. Okay, so transaction 3 is done. I'm going to now schedule transaction 4 in the open queue for the 3rd resource. Stepping ahead, now transaction 1 is done, and there's a pending result posted for transaction 1. So now, in the pending results queue, I can start processing that while also adding transaction 5's execution to the top thread because it's open. And so on and so forth. So, yeah. Now, we're going to take a look at this in a little bit more depth because one of the questions that we often get is, well, what happens if there's a collision? Because, like, isn't that a problem with parallel execution? Because ordering sometimes does matter. Okay, well, we'll take this as an example. Transaction 3 is dependent on the outcome of transaction 1. And let's just assume that this is all about transfers of USDC. So the starting point before transaction 1 has ever occurred, we're just going to say I have 1,000, Alice has 0, and Bob has 300. But within transactions 1 and 3, I'm transferring each of them 100 USDC because, either I'm generous or I purchase something, maybe a very expensive box of pizza from each of their pizza stores. What we expect to happen is that the outcome of these transactions is on the right here. So I now have 800 left, and each Alice and Bob have incremented by 100. Okay, so let's try to put this into practice. The way that pending results work is that it will capture the assumed inputs, the starting inputs of a transaction, as well as the resulting outputs at any given time. So in this case here, when I started the transaction execution of both transaction 1 and transaction 3, the starting inputs were exactly the same, which was the state of the world before at 1,000 USDC for me, 0 and 300 respectively for Alice and Bob. and then the resulting outputs. So now, as we're going through each of these pending results and committing them to state, I'm going to make sure that the committed state actually matches that of the assumed inputs in the pending result. In the case of transaction 1, they match. Excellent. So I'm going to update my committed state to now 900, 100, and 300 respectively. Transaction 2, don't need to worry about that, not related. Transaction 3 now, we're seeing a conflict. 900 versus 1,000. So in this case, like, what do? It's not going to be committed. We have to reschedule it. It has to be re-executed. So going back to this example, we'll say, okay, we realize we need to re-execute it. I'm just going to re-execute transaction 3 again, and I'm going to slot it into the next available resource here. The time it takes to execute this resource is a lot faster. You'll notice the bar is much smaller. Why? Well, because we have the memory already committed to state. It's in RAM, it's very accessible, it's very quick. The biggest bottleneck of execution for L1s is not the execution itself, it's actually in getting the state I/O. We don't need to worry about that with re-execution because it's already there. And in reality, the more likely case is that transaction 3 would be more or less like immediately re-executed here instead of like a wasted resource like that. Okay, so committed, and we're now happy with the resulting state. So TLDR for optimistic parallel execution, we're going to assume that there are no collisions to begin with. When there are, we reschedule. So worst case scenario, a transaction is rescheduled once and executed twice. However, recall that the second time around, it's honestly very, very quick. All right, next one, MonadDB. I'm realizing I'm running a little low on time here, so I'm going to try to speed up. MonadDB is a custom-built database. Why do we need a custom-built database? There's tons already. Well, Merkle-Patricia trees are rather complex. They're not really the type of data structure that you see out in the wild outside of in blockchain. I just took a generic Merkle-Patricia tree graphic here that I think kind of illustrates its complexity. And not only does, in EVM, not only is there one MPT, there are multiple MPTs for, like, there's a receipts tree, there's a transaction tree, there's a state tree. It's a lot of trees. Tries, maybe. All right. So a lot of blockchains right now will use out-of-the-box commodity databases, which operate under an LSM model. So the structure there is a little bit different. It's key-value store. It's very efficient from a generic perspective because it works with a lot of different data structures. However, again, Merkle-Patricia trees are complex. With Merkle-Patricia trees, values are stored at the leaves. And with an LSM tree, there is complexity aligned with storing things in LSM tree. Why? Because for every single node that we traverse in a Merkle-Patricia tree, it requires a full traversal in an LSM tree. So it adds a lot of added complexity if we're doing this again and again and again for MPT data. This is both for reads and writes. TLDR is that MonadDB is redesigning a database that is specific to the Merkle-Patricia tree structure so that it is natively stored and also then natively written and read. Much more efficient. Uses the latest in I/O ring research. And yeah, I will move on to the the last one, which is MonadBFT. There's actually a new paper published about MonadBFT last week or the week before, 2 Fridays ago. It is a new BFT algo, and it offers a lot of assurances that don't exist in existing BFT models today. It's fast consensus, and it's with linear complexity, which I think is honestly pretty key, because network and communications is oftentimes that's not the word. Usually some order of magnitude more than just linear. Okay. One of the unique things that MonadBFT offers is tail forking resistance. And, okay, I have 21 seconds left. Do I have more time? A little bit more. Okay, sorry. Okay, I'm just going to speed through this. You guys can read the paper. You can read the blog from category.xyz/blog. I want to touch upon testnet just a little bit here. So we have testnet is live. In case you haven't checked it out yet, I would recommend hopping over there, grabbing some testnet tokens, and taking a look around. As of today, there are over 10 million transactions that have been deployed across apps, NFTs, games, a ton of stuff. I checked this morning. There have been over 925 million transactions transacted on Monad testnet, which is kind of insane, since its inception just 2 months ago. Of the 220 applications that are deployed, you can check it out on an ecosystem page here, 118 of them are actually from APAC-focused teams. So this illustrates a very strong a desire for APAC builders as well as APAC communities to really explore a new ecosystem. Within APAC specifically as well, Monad has worked with 25 different teams for Monad Madness, which is a fun pitch competition, one that was recently hosted last week as well with 5 new winners, and also several new programs that Monad Foundation hosts throughout the year. There have been 42 to date since last year alone. Also a very big community within Monad ecosystem, 12,000 members on Telegram, 600,000 in Discord, and 64% are APAC communities as well. And it's also the fastest growing region, led by the Mandarin community, and several also in Indonesia, Japan, Thailand, Vietnam, Korea, and India. Lastly, I wanted to show the global network because I had talked about a distributed validator set. This is the current set right now with the 72 across the world. And as noted, a lot are in APAC as well. And that's it. Thank you, everyone, for your patience.